Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be the second of my Tactica Tutorialis teaching videos, and today's lesson is going to be an A-level physics topic looking at electric fields per commenter request. So this forms part of Unit 7 of the AQA A-level physics, but it also comes up a lot if you go on to degree level physics, or if you're following another A-level physics spec. It is certainly something I think you should know. And if you're interested in extending your understanding of electricity and things like that from GCSE, then this might be an interesting sort of follow-on point. I was tempted to just pick up from our lenses lesson last time. I chose not to because I'd rather do these lessons per commenter request. So this lesson is something that was asked to be done by a commenter. So I'm going to do that, and I will continue to do that, favouring the comment requests over everything else. So if you have a lesson that you'd like me to do or a topic you'd like me to cover, please do let me know in the comments below. It is the easiest way for you to get a lesson that's taught by me if that's what you want. So what are we doing today? Today, as I say, is about electric fields, and that's going to be broken down into 3 segments. First, we're going to start by looking at some of the mathematics behind electric fields. We're going to look at Coulombs Law, which is going to involve the inverse square law, and we'll relate that to create the strength of an electric field. We'll derive that formula. Second of all, we'll look at field lines and using that understanding of electric field strength to understand how electric fields appear when we draw them and what that means for charges within an electric field, which is something you may have met already. Certainly I did it with my GCSE triple class in the past. And then once we've done that, we're going to look at electric potential and potential energy. And that is our link to GCSE physics, where you look at potential difference or voltage, depending on which sort of language you've spoken, and energy within charges and circuits, which is something that you do at GCSE, or at least certainly I think you do. So that's going to be everything we're going to cover. So it's going to be a bit of maths, a bit of drawing, and then a bit more maths. Sort of how we're going to break this lesson down. I hope you found it useful. Feel free to ask some questions as we go, because I'm going to be using the Premiere feature for this because I found it quite useful. So if you have any questions, ask as we go, and I will do my best to help you in the live chat, or leave them in the comments because, well, the comments are there and I can help and you can help each other. So without any further ado, let's get started with a little warm-up activity, and we'll do Coulomb's Law and the rest of electric fields. So, to kick today's lesson off, I want to quickly recap / introduce something known as the inverse square law. This may be a term you know. If you don't, then you're going to get to know it throughout the field's topics. So certainly it's worth knowing regardless. So the formula goes using a proportionality, and the question I want you to try and answer goes as follows. State the inverse square law relating a variable which I'm going to call A to another variable which I'm going to call B, i.e. A is proportional to something, where that something is what we would call a function of B. So some function of B is going to be proportional to A, and that function is known as the inverse square law. So A is proportional to this function of B is the inverse square law. What is that function? What is it? Think about the name of it, the inverse square law. You might be able to apply that. I'm just going to give you 1 minute just to have a go, write it down somewhere, and then we'll go over it. So yeah, if you're new to the videos, pause the video, have a go for a minute, and then once you're happy, restart the video and we'll go over the answer. All right, hopefully you've had a go. So we need to break this down into 2 sections. One is the fact that it is an inverse law, and the other that it is a square law. So if we take the first one, we might say it's a square law. So because it is a square that relates A to B, and we know A is on its own, you might have said A is proportional to B squared. And if it were just a square law or a quadratic law, you'd absolutely be right. However, that was ignoring this inverse. Now, when you say something is the inverse, this is something you'd learn from particularly doing maths. This is equivalent to saying 1 over something. So if something is the inverse of something, it is 1 over. So the inverse of, say, x is 1 over x. So we need to take this square and make the inverse of that square. So that's not quite correct. You would say, and your answer would be, that a is proportional to 1 over b squared. Or you would say that, if you prefer your notation with negatives, b to the power of minus 2. That is the inverse square law. And you're going to use that quite a lot as part of this lesson and our planned follow-up lesson I want to do on gravitational fields, which is another thing someone's asked me to do, which is what I'm going to. So that's the inverse square law. A is proportional to 1 over b squared in general. Now, there's going to be a second question that, again, sort of, if you're an A-level math student, you'll probably know this. But I just want to make sure that everyone's got it before we carry on with the rest of the lesson, because it is something that's going to come up toward the end. And that is, express a function a of x as the differential of a function b of x with respect to x. So that's a slightly wordy term. Express a function a of x as the differential of a function b of x with respect to x. So if you've done much A-level maths, this will be absolutely fine to you. If you haven't, then it's a little bit trickier. But again, pause the video, maybe have a quick look online if you don't know the term differential, and have a go. 1 minute. All right, lovely. So you should have paused the video, had a go, and now we're back. So when we say differential, it's the equivalent to saying how much does b change per change in x is equivalent to a of x. So if you're at lower school, you might have seen acceleration equals change in speed over time. A equals delta v. Actually, I need to write that somewhere else. But you might have seen that, which would then be expressed, for example, as A equals delta V over delta T, or A equals delta V over T. You may have seen that. Certainly I've seen that at GCSE level, and I think you will have too. That is the sort of categoric, simplified form of differentiation. So the answer is just mainly down to notation from there. So we know that we've got the change in a function b of x with respect to a change in x. So when x changes, how much does the function change? That is the equivalent to a. But we don't write it in delta form unless we're talking about it in terms of infinitesimal things, which is like super small stuff, or if we're being a bit more categoric. So the general formula we'll use, and you will see this again and again and again, particularly in A-level maths, and certainly if you're going to take physics at a higher level, is d by dx. You may also see it with a slanted d. That's for partial differentiation. I'm not getting that today because we're not going to... Actually, we might touch on that later, but that's the basic formula for differentiation. A function a is db by dx, therefore a is the sort of the rate of change of b with respect to x. I know it's a bit mathsy to start the lesson, but those are a couple of key formulas that you are going to need to know whilst we do our electric fields, and certainly we're going to need the inverse square law very early, and you'll probably need the differentiation a lot later, and you'll probably need some integration as well, but that's year 13, at least when I did it, so we won't cover that too much today. So let's start the lesson off by doing about Coulombs Law. The first part of today's lesson, now that we've got ourselves a little bit familiar with some maths, is going to be Coulombs Law. And Coulombs law essentially allows us to derive the strength of an electric field. As what an electric field is, it's a little bit more nebulous, but hopefully this will explain what's going on and be able to see it a bit more as the lesson goes by. So, Coulomb's law is based on the idea of 2-point charges. Now, a point charge, for those who haven't come across the term, is a charge that is entirely concentrated at a single infinitesimally small point. In essence, why we use point charges is to get rid of having, say, a ball of charge and having charge densities and it varying by distance. It's basically a simplification to get charges into a more natural and easy to use form by concentrating them all in one place. So we have two of these point charges. I'm going to call them Q1 and Q2. You'll be used to Q because Q is what we use for charge back at GCSE, and you might also recognize Coulomb because Coulomb was the unit of charge, and it still is. So each of these charges are there, and they're separated by a distance that I'm going to call R. And for this to work, we then need to assume that there is a force in play, and we can see that. So if you have two opposite charges near to each other, so for example, two protons do not just sit next to each other quite harmoniously. They repel each other. If I have a proton and an electron, they don't just sit there quite harmoniously, they're attracted together. Granted, there is some separation that comes into other forces, which we'll probably not get to in this lesson, it's sort of a different topic, but there is an attraction between them. So charges attract and repel each other based on their positive or negativeness. Positivity, negativity is a better word. So if you've got two positives, then you get repulsion. If you have two negatives, you get a repulsion. If you have positive and negative, you get an attraction. And we can then measure that force thanks to Coulomb. And Coulomb derived / worked out an inverse square law for the force on, say, Q2 due to Q1. So if I'm looking at Q2, Q1 is going to put a force on it and push or pull it around. What is the size of that force going to be? Well, it's an inverse square law, and it is as follows. The force from one on the other is proportional to Q1 multiplied by Q2 all over R squared. This is where our inverse square law comes in. As you can see, it's proportional to 1 over the square of the distance, or the radius if you like, between the two charges. That's where inverse square law comes in, and we know that it's proportional to the magnitude of the two charges. Obviously, if you've got positive negative, then that'll create a negative number, which creates an attractive force. And if you've got two positives or two negatives, you get a positive force, aka repulsion. Now, this constant of proportionality is just a number you're going to need to know. And it comes up a lot. You'll see it, I think it's on formula sheets quite often. And it is given as 1 over 4 pi epsilon naught, or epsilon naught, depending on how you say it. That is also known as the permittivity of free space. It is just a number. I think it's 8.85 times 10 to the minus 12 giant pile of units. Do you need to know it off by heart? No, it's on your formula sheet. Do you need to know this formula? I think it may be on your formula sheet, but it is one that you should probably be able to do very quickly off the top of your head. So that's our constant of proportionality, and then we just add in our things it's proportional to, Q1, Q2 over R squared. That, right there, is Coulomb's law. The force from one charge on another is equal to 1 over 4 pi epsilon naught, Q1, Q2, all over R squared. That's Coulomb's law. Now we get a little bit more clever, and we need to apply another part of Coulomb's law. So I'm going to rub off this top section. I apologise, but I'm going to need to. So I'm going to leave the formula for the force up. And what we need to now do is define the electric field strength. Field strength. And I'm going to call that E. Now, both the force and E are usually vectors, so I should, if I'm thorough, be writing these as vectors. I'm going to neglect that notation for now because I'm just trying to get this across. However, certainly if you go higher with this, you will absolutely need to be treating these as vectors rather than scalars. But to define the electric field strength, what we say is that E is equal to the force per unit charge. So, if the electric field strength determines the amount of force applied per unit of charge that we have being pushed, if you like, by the field. So if one charge is pushing another with a certain amount of force, if you divide through the amount of charge that you've got from the force that's being applied, you get how powerful the electric field of your pushing particle is. And every single charged particle has its own electric field strength. So if I come back to my earlier scenario where I had Q1, Q2 separated by a distance r, I wanted to find out the force on Q2 due to Q1. So to work out the electric field strength of, say, Q1, I would have to do, so the electric field strength of 1 is equal to the force applied by 1 on 2 all over the charge being pushed. That is Q2. But you could also do this the other way around. So the electric field strength of 2 is equal to the force between them divided by Q1. You could do this both ways around. And that leads to our general formula of the electric field strength is equal to 1 over 4 pi epsilon naught Q over R squared. I've generalized to just Q because it's true for whatever the charge creating the field is. So it may be that this is the electric field of Q1, so you'd have Q1 there, the electric field strength of Q2, so you'd have Q2 there. But in general, that is the formula that you're going to need to know. So in the boxes are the three formulas. The force between two charged particles, 1 over 4 pi epsilon naught, Q1, Q2, all over R squared. You then need to apply this definition of the electric field strength, where E is F over Q. You may also see, I'm going to write this down here in a different colour. You will also probably see it written as F equals QE. That's the more common notation for this law, is that one. So F equals QE. In fact, I've certainly used that before in the Lorentz force law in one of my old videos. So F equals QE rearranged gives you E equals F over Q. You plug that in and your general formula is the electric field strength for a given charge is 1 over 4 pi epsilon naught times the value of that charge divided by the square of the distance between the two charges in the first place. However, what if you only had one charge? So let's say for a second I had one charge all on its lonesome. Because let's say we're going to remove Q2 now, and we're just going to say, what if I only had one charge, which we're going to call Q? How do I work out its electric field strength? Well, you just pick any arbitrary distance and say, that's R. Or you might go that far and say, that's R. Or you might go that far and say, that's R. So it is easy enough to say at a certain distance, the electric field strength is equal to 1 over 4 pi epsilon naught times Q all over whatever the distance you've been given is squared. In fact, let's do a little worked example, if you like, and we will hopefully be able to see this in full. Do a little worked example. So let's say I have a charge of, let's go with 1.6 times 10 to the minus 19 coulombs, because that's an electron. sat 1.5, let's say, millimeters from another charge of, let's say, 3.2 times 10 to the minus 19 coulombs. So you've got, let's say, an electron sat next to a nucleus of helium-4. Just for argument's sake, calculate A, the force on the electron, on of E, and we'll call that one Q, on the force on the charge E from the charge Q, and then B, the electric field strength of Q at that point. That's a lot of words, but that's probably not an unfamiliar type of exam question. Right, I'm going to reword that a little bit to be a bit more like we're on an atomic scale. So let's say that's nanometers. We'll go down to a slightly more reasonable scale, and we'll say that that is nanometers rather than millimeters. Makes a little bit more sense. So a charge of E equals 1.6 times 10 to the minus 19 coulombs is sat 1.5 nanometers from another charge of Q equals 3.2 times 10 to the minus 19 coulombs. Calculate the force on E from Q, and then the electric field strength of Q at that point. So where E is, so at that distance there. So give yourself about 5 or 7 minutes to have a go at that task, because I realize I've been talking for quite a long time, and then we'll go through the solution together, and hopefully you'll get a bit better understanding of how we use Coulomb's law. Good luck. Okay, hopefully you've had a go at that. Best of luck if you did, and I hope that it wasn't too unmanageable. Let's go through the solutions now. So, question part A asks you to calculate the force on E from Q. So force from Q onto E, as I'm going to write it. You might prefer to write the other way around. That's how we're going to do it. So first off, we need to write Coulomb's law in general. So we'd say that is 1 over 4 pi epsilon naught Q1 Q2 over R squared. In this case, that is equal to QE over 4 pi epsilon naught R squared, where R was 1.5 nanometers, which you will need to convert into good old SI units of 1.5 times 10 to the minus 9 meters. Now, at this point, you should be able to do that off the top of your head. You're an A-level student, so this conversion you should be able to do all the time without even thinking about it, but I'm going to write it there for good habits. So we then just need to plug in our numbers. So if you got that, there's a mark. The next thing we need to do is plug the numbers in correctly, which is 1 times 3.2 times 10 to the minus 19 times 1.6 times 10 to the minus 19 all over 4 pi times 8.85 times 10 to the minus 12. You might have had to look that one up. Times 1.5 times 10 to the minus 9 all squared. There's a mark for plugging your numbers in correctly. You might have put your numbers in it the other way round and done it that way before formula, but that's what you had to do, plug that in, and I've stuck that into my trusty calculator. Other variants are available, and you see I get an answer of 2.046 times 10 to the minus 10. So I get an answer of 2.05 times 10 to the minus 10 newtons. Now, if I'm wrong, I am 99% sure that you will be correcting me right now, but that's what I got from sticking it in my calculator, 2.05 times 10 to the minus 10 newtons. I think that's right. So the second part of the question asked you to calculate the electric field strength at that point. So I'll just leave that there so we have a word solution. So if you need to take it down, pause the video, take it down now. Good. Now part B asked you to calculate the electric field strength, and there were two ways you could go about doing this. So part B asked you to find the electric field strength of Q at the point R. Now, you might have done this using the same method as we just did and gone 1 over 4 pi epsilon naught Q over R squared. Because that is the formula for electric field strength. And if you did it that way, you are absolutely within your right to do so. It is very good practice, but it comes with a very minor risk of mistyping something in your calculator and thus slowing down the process or making a mistake and losing yourself a mark. So the other way you could do it is to say that E at Q is equal to the force between E and Q all over the charge E, because E is the 1.6 10 to the minus 19, and both of these answers should give you the same thing. I'm going to stick this in my calculator now. I'm just going to do the answer, that's the wrong button, the answer divided by 1.6 10 to the minus 19. You see I'm not doing any fancy tricks, and I get an answer of 1.27 or 1.28 times 10 to the 9. 1.28 times 10 to the 9. Now, at this point, you might be slightly wondering to yourself, Tactica, what's the unit of electric field strength? Because I haven't given that to you, and it isn't necessarily that intuitive. The obvious thing you might say is, oh, I've just had newtons and I've divided it by a charge, so I should say newtons per coulomb. And technically, that's not wrong. I'm not going to give the unit to you now because it's going to become, actually no, I will give it to you now, but it's going to become a little bit clearer when we do this later. So the unit you wanted, if you want to know, and we will talk about this later, is volts per meter. That right now will make absolutely no sense to you unless you've seen this topic before. But by the end of the lesson, we should be able to explain why the unit is volts per meter, because we're going to talk about electric potential. But we're not there yet. So the next part of the lesson I want to do is to talk about field lines and how they are drawn for electric fields. So I'll give you a second to take down this answer, and then we'll move straight on. Okay, now we need to look at how we draw electric field lines and what that tells us about, well, everything really. So, electric field lines are drawn based on usually point charges. Now, I'm not going to talk here about capacitors, parallel plates, or anything like that. That is another topic for another day. If you want me to do capacitance, I'll do it, but that will introduce a slightly different type of electric field line. But it still follows the same rules that we're going to abide by here. So, the main thing to think about with an electric field line in terms of how you draw it is following a couple of simple rules. The first one is a field line is an arrow. So we're going to draw arrows like that, lines with arrowheads sort of in the middle, to represent our field lines. That's the first thing. That's how we're going to draw it. That is now an electric field line. But the way a field line is drawn is that field lines move or travel / are drawn, if you like, from positive to negative. This is a rule that comes up quite a lot in electricity, same with current actually. We just assume everything goes positive to negative. It's just the way we do things, and it makes our lives easier as a result. If you want a reason to why we draw it that way, you might say, if you had these charges, in what direction would a positive charge move were it in that electric field? And that would then allow you to draw the path that it would take and thus what the field lines are, if you like. So we now need to apply those two rules, and I've got two charges here. I've got a positive charge and a negative charge. Now, for the moment, we're going to treat them as two entirely separate universes. They're not actually next to each other. There's one in some isolated corner of the universe and one in some other isolated corner of the universe. They're not actually this close. We'll do that in a minute. So, if I have a positive charge, and I've said that my arrows move and are drawn from positive to negative, which way should I draw my arrows, do you think? It's a little bit hard to show on an individual charge, but if you think about it like it was a point charge, then you would treat it as though all the electric field was coming out of that point. So you would draw it via a series of arrows like so. Now this is what's also known, and you'll see this with gravitational fields as well, whether I do it, which I will, as a radial field. So these fields are what we call radial. You might have been able to get that hint from the fact that we were talking about R earlier in Coulombs Law, but they are radial fields because they spread out from the source in all directions. And each of these I could draw a bunch of infinitesimal circles at a given radius, and the electric field would be constant across that circle at that radius. Then at the next circle with a different radius, the electric field will be constant there, but different to the field there. It's a radial field, so it spreads out in all directions. Now, what if I had a negative charge? Well, we apply this rule, moves from positive to negative. So you might say, therefore, that all electric field lines arrive at negative charges. So we do the same thing as this. We've got our arrows coming, or our lines coming like that. But this time, our arrowheads will be pointing inwards. Because you might say that this is the sort of source and sink, which is a terminology you might come across in some areas, where all the electric fields would arrive at, and so all the electric field lines are going into it rather than out from it like we had with our positive charge. Now, obviously electric fields can exist on their own. You don't need to have two charges together to get an electric field. Magnetic fields, you do need two. It's called the magnetic monopole problem. It's a uni thing. But if I have a radial field around each of our point charges, positive, the field lines are going outwards, and on a negative charge, the field lines are going inwards. Now, here's where things get a little bit clever. What happens if I have a positive and a negative charge together? So if I have a proton and an electron sat next to each other, what would the field lines between the two of them look like? Because the field lines have to connect together in order for there to be sort of a shared field of attraction and repulsion between them. In fact, that's sort of the actual final point. And that is that field lines connect. I haven't got any good space for it, but I'll be able to draw it out. So I'll write it here. Field lines connect between charges. So now if I know that, what would the field line between my positive and my negative charge look like? Just give yourself a minute or two, have a think. Maybe if you've got a piece of paper or a whiteboard, I do love my whiteboards, have a go at drawing it. So set up a positive, set up a negative, draw them next to each other, and think about what the field lines are going to do. 2 minutes, pause the video, then come straight back. All right, so hopefully you've had a go at that now. Time to get some answers. And honestly, it's not possibly as complicated as you might be thinking. It's actually dead simple. If you have them drawn like this already, which is certainly a good place to start, then you just apply this to this using this. So you take the positives, goes out the positives and into the negatives, connecting the field lines together. In fact, you've done 95% of the work. All you've got to do, actually I'll draw this in a different color because then you can be able to see the solution, is the field lines connect together just like so. Not going to go too close, I don't want to ruin my blue pen. The field lines connect together. So this one comes out like this, and it comes across like this. This one comes out like this, it bends around, and it comes together like this. And this applies to all field lines. So you might have another field line, which is here, that goes like that. And you have another field line that's here, and goes like that. And another field line that comes out here, and into there. Or out of here, just got room to sneak it round, and across like that. And even the field lines out here will eventually connect together. So this one will come around, I'm just going to go off my screen, come all the way out here, around and around and around and around and around, and into that one. All the field lines connect together. That's the really clever bit. It's a little bit awkward to show in full, but if you can just focus on that bit, like inside my hands, that's the idea. That is the electric field between two charges. That's it. And you might be able to say now and apply that what I said earlier about the way a positive charge would move in the electric field. So for example, let's put, I wish I had my red pen. I've lost my red pen and I really want to go and get a new one, but I can't leave my house. So if I had a positive charge just sort of sat right there in the middle, if I follow the arrows, it's going to move sort of in this direction. It's going to be pushed away from that and move in that direction, which is exactly what you'd expect to happen if you had two charges. So you have a positive and a negative, and you put, say, a positive plate there and a negative plate there, which is what you do with capacitance. You create a parallel plate electric field, positive to negative, you fire your positive particle through, it will be pushed away from the positive and toward the negative. In fact, let's actually draw that because that is a point that you probably need to know. So, have a second if you need to take that down. Now let's actually just show it very quickly in terms of trajectory. The last point on this sort of subtopic, and then we'll move on to talk about potential. So if I had, and you're maybe familiar with this if you did triple science, certainly I've done this with one of my triple science classes. If I had a positive plate up here and a negative plate down here, what would the electric field lines look like for this field? Have a go at it for a minute, and then we'll come back. Okay, I had a chance to pause the video. Well, the field lines, actually, quite simply, I was just going to go a little something like this. Straight, cross, and down. Positive to negative. We're not going to talk about the edge effects, all like this jazz over here, though I'm going to draw them on for completeness. That's what your electric field looks like. And if I was to fire have I got room? Yep, a positive charge into here, the trajectory it would follow, because it's pushed away from the positive and toward the negative, its trajectory would look something like that. Assuming it was heavy enough to get through the whole field. It might maybe just travel something like that, or like that. It would be pulled downwards and pushed by the electric fields toward the negative plate, because it's attracted by the negative, repulsed by the positive, and therefore moves according to the electric field lines. So that's field lines. That's everything on that topic. We've got one more bit to do, And it's going to get a bit more mathsy again, I'm afraid. We're going to talk about potentials and we're going to talk about electrical energy. All right, so the final part of today's lesson is looking at electric potential and also at potential energy. And we're going to break that down into two subsections, though they are very much connected. Now, the first one we're going to need is going to rely on having our two formulae. So I've written them out again. Our force is Q1 Q2 over 4 pi epsilon naught r squared, and the electric field strength Q over 4 pi epsilon naught r squared. I've slightly condensed them because it fits better on my whiteboard. If you prefer to write them in long form, I'm not going to hold that against you. So, in order to work a few things out, we're going to need to call back a little bit to GCSE physics. And for that, well actually GCSE A science actually. And for that, we're going to start by looking at what we call work done. Now, you might have seen work done before. In fact, you will have done if you're an A-level physics student. You'll have definitely seen work done before. And you will hopefully remember that the work done is equal to the force F times, I'm going to use S for distance. You may prefer to use D. I'm going to use S, force times distance. And we can then apply this and take it to look at, well, this formula right here. So we might say the work done to move Q2 from infinity to a distance r from Q1 equals F times R. Now, that might look a little bit like I've done some space magic. You might be going, Tactica, why is it force times R, not force times infinity minus R? Well, the idea is that if you were a distance infinitely far apart, then there would be no force on the Q2 due to Q1. They'd be infinitely far away and the fields would basically not affect each other. The force, if you plugged infinity in there, would be basically zero. You'd be dividing by infinity, so you get zero. So what we say is that the amount of work it took to pull our charge in from infinitely far away to sit a distance r away from Q1 is equivalent to, you might say, having the two next to each other and the work required to pull the two apart so that they were a distance r apart. Because you know F, so when r equals 0, you've got infinite force, F equals infinity, 0 force, therefore the sort of distance to pull them apart, it works. That's what I need you to take away from that. It's a little bit messy to explain it as a work done like that to link it to this, but that's the formula you're going to need to know, and then we plug that in. Say that the work is equal to Q1, Q2 over 4 pi epsilon naught r squared times r. And quite simply, I can just cancel out the squared, I can cancel out the r, equals Q1, Q2 over 4 pi epsilon naught r. And we don't call that necessarily the work done, because work done is kind of a nebulous form of energy. The work is done to pull it in, and then that energy is stored in some way. You might have seen energy stores if you're one of the younger members of the audience, and we call that storer as the potential energy, or the electric potential energy, which I'm going to call U. So I'll get rid of that bit from the middle, because that's a bit of nebulous definition, though I think it's useful to know. And I'll write that in bigger. So the electrical potential energy, U equals Q1 Q2 over 4 pi epsilon naught r, where r is the distance between them. And that's the first of the two big formulae that we're going to do in this section. Bing, bang, and bosh. Now, I know my U might look a little bit like a V because it's a capital U and I'm bad at writing. Make it absolutely clear that that's a U, not a V. Because if it's a V, you're getting it mixed up with something else. And that requires calling back to our second little bit of GCSE physics. You might have seen the volt. So 1 volt equals 1 joule over 1 coulomb, aka V equals E over Q. E equals QV is definitely a formula you meet in terms of the energy in a circuit. It's the charge times the potential difference or the voltage, depending on which version you use. And therefore, we can plug this formula into here, which is really, really clever. So we then say that because E is an energy, so V equals U, I'm going to be really careful, I'm going to call that U, over, we're going to divide, doesn't really matter, I'm going to divide by, as the potential of 1 is U over Q2. And you don't really need me to plug this in, you could just do that division for yourself, but I'm going to write the answer now. So do that division, and that sets up the potential. So the electric potential this is being measured in joules, equals V, right, really clear that's a V, equals Q over 4 pi epsilon naught R. Okay, I'm going to just make that really wide so it's clear that that's a U. So those are the two formulae that you're going to need to take away from this, and how you get there, I have worked through. You might need to scroll back a little bit. So the electric potential energy is the energy stored due to the work moving a point charge Q2 from infinity to a distance r from a charge Q1. And the electric potential, V, is the energy per unit charge. Same idea as the electric field being the force per unit charge. Now, given how I worked this out, can you see where I might be going with that thing? I hope you can. So I'll give you a second to take that down. And this is measured, of course, in volts. So I'll give you a second. And now we're going to put all of this, and all we did between these two, and these two, and these two, and these two, together to create one final bit of formulae that I think you'll need to know. I'm going to clear as much space as I can. And this is where that differential stuff, or derivatives, from the start of the lesson start coming in useful. So we've just seen E is Q over 4 pi epsilon naught r squared, and V equals Q over 4 pi epsilon naught r. Brilliant. So what you might be expecting me to say right now is that V equals E times R. You might be expecting me to say that. And you'd not be wrong. On a basic level, that is how you relate the two. However, there is a slightly cleverer way that we relate these two together using differentials. So we need to work through how a differential works very briefly. So let's do that. But I'm going to do this the other way round. So we say that E is delta V over delta R, if you prefer. Now let's plug that in. So remember our formula for a differential from the start. We said that A equals dB by dx. You might remember that from the start. Well, now we can say that A is equal to our electric field, B is equivalent to our potential, and X is the distance R, or the radius R, as we're now going to be working in, because we've got rid of the second charge, so separation doesn't matter. Radius is what matters. So we say that E might be dV by dr. However, when you do a differential, the way you do it is a little bit sneaky. So let's just do dv by dr for a second. So when you do a differential, we'll say that v is equal to a r to the minus 1, because it's 1 over r, so we say power of minus 1, and this is just a constant, so we're just going to call it a. Now dv by dr, what you do is you multiply by the power of r, and then you decrease the power of r by 1. So you'd have minus 1 times a r to the minus 2 equals minus a over r squared. Do you see the problem? Because E equals a over r squared. A is q over 4 pi epsilon naught. So if E is a over r squared, dv dr is minus a over r squared. We're missing something from here, and that is a negative sign. So the potential and the electric field are related through a differential equation, where the electric field at any point r is given by the differential of the potential at that point r with respect to r. You can break this down further. So if you want to do it in x, y, and z, you might say that E along the x-axis, you'd have the partial differential of V by dv of x, y, and z by dx, ey, dv by dy, and so on and so forth. That's a little bit more messy practice, but you can look into partial differentials if you are aware of them. They certainly still apply. That differential equation is not strictly necessary unless an exam asks you to do it. You need to be able to do a differential and explain why that gives that in terms of minus signs. You may also want to see that v is therefore going to be minus the integral of e dr. If you really care, I'm going to write that there and then get rid of it. But I don't think you'll need to see your integrals at this stage, but it's worth knowing because I think it's useful. So that's that. So all the formulae together then, let's get them all written down, and that's going to be your last task for today. Be a little summary, and then if you want a little bit of homework to practice on, then you are welcome to. So your plenary task, your last job for the lesson, is write down the formulas for F, for E. So you know what, I'll just get rid of F of R. F of R is a bit silly. So F equals what, E equals what, U equals what, and V equals what. Those are the 4 formulae that you're going to need to know, and they'll probably be on your formula sheet, but that's your last task, is to be able to write them down. We did some calculus with this one earlier. The same principles apply here. You just got to plug your numbers in, same sort of idea. So there's your final task. I think you'll only need a couple of minutes. Write them down. But the one last thing is to give the unit. So hopefully you'll now understand where we got the unit of electric field from earlier. And these units you've all seen before. So there's your final task. I'll just write underneath. So unit, 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 and unit. Because again, we're physicists, we need to get good at using units. So I've got to write the formulas and their units, 2 minutes. Okay, hopefully you paused the video, had a go, and come back. So let's write these last answers down. So the force between 2 particles, Q1, Q2, over 4 pi epsilon naught r squared, measured in newtons. Nice and simple. Big tick. Now, the potential energy was equivalent to timesing the force times the distance. So F times R. So we had Q1, Q2 over 4 pi epsilon naught R, if you will. And that is measured as an energy in joules. Your electric field was by doing force divided by charge. So we'll get rid of the notation and just say Q over 4 pi epsilon naught R squared. And the potential difference by doing U divided by charge is Q over 4 pi epsilon naught R. And because that is potential equivalent to voltage, that is measured in volts because it's energy per unit charge. E over Q is volts. Now this one, you might remember I gave you the unit earlier in the video as volts per meter. And if you remember that E is dV by dr, which is roughly equivalent to delta V over delta R, you'd get that that's measured in volts, that's measured in meters, so volts over meters, volts per meter, or volt meter to the minus 1. Either or will do. So that is the entire lesson summed up in 4 equations, well, 5 equations if we're being picky. That's everything that I think you need to know. So I'm going to set you one last homework question. If you want some homework to practice at using these formulae one more time, let's set some homework very briefly. So I'm going to say I have a point charge of Q1 equals 4 coulombs is positioned 3 meters from a second charge Q2 equals 5 coulombs. The first part is going to be calculate the potential energy U. Now it's going to be quite a small number, so don't worry if you get a really tiny number because of, or maybe a really big number, quite possibly. And part B is going to be calculate the force on Q2 from Q1. And part C is calculate the field strength of Q1. So those are your homework questions. If you want to challenge yourself, then you can also have a go as a little thing about drawing trajectories. If you want to go back to that little bit of the lesson, you can talk about that a little bit. But make sure you go back through the lesson now, take any notes that you've missed or add any additions from a second listen through. So thank you very much for your time and your work during today's lesson. I do hope you found it useful and informative and hopefully not too dull because I've tried to show all the stuff. But at A level, you do kind of have to get into a bit of the nitty gritty. So that is all for today. The next lesson I'm planning to do is on gravitational fields. So make sure to keep your notes from this lesson and bring them to that one because they do sort of link together a little bit and I think you'll find it quite interesting. So thank you very much for watching. This has been Tactica Imperialis and this has been A-level physics, electric fields as a bit of a lesson doing about Coulombs Law, electric field strength, field lines, potential and energy. Thank you very much for your time. Hope you've enjoyed it and I'll see you all again. Bye for now.